So this is my first presentation proper, so please bear with me. There we go. Okay. Yes. Yeah, so that's the solution, I guess. Moving on. My name is Alve Björk. I come from the Kingdom of Sweden, and there I am a perpetual student at Uppsala University. Some things I like include tea, cats, murder mystery television shows, mainly British ones actually, and computer science, of course. But for the last half year, my life has mostly revolved around catering for this little person, which so the competition was very good in that it gave me something stimulating to think about for a while. So the contest this year, as Brian told you, yeah, it's still 2 phases. The first phase is one-liners, even though admittedly some lines are quite long. Phase 2 is mostly couple-liners. I didn't quite manage to do that for all of the problems, but there were 3 tracks this year you could choose from. 3 problem sets. The first one was on cryptography, the second one on physics, and the third on neural networks. Each problem set had a set of problems, obviously, and each problem had a set of tasks. I don't have time to speak about everything. And if I did, I think I would bore you to death, so I'm not going to do that. I've selected a few problems I will present. But I've actually written slides for most of them, so I don't know if you have sort of looked at the problems, but if you have, I can probably bring that up at the end if you have requests. This was the first problem of the physics part. You were asked to calculate the aphelion velocity given the perihelion velocity and the perihelion distance. I have no idea what this means. I think it relates to planets somehow. It's science. Luckily, you're provided with a formula, and that is math. I know math. And it boils down to solving a quadratic equation, which all of us have been able to do for quite a long time, so I'm not going to dwell on that. And you were actually also supposed to round the answer, but then you needed a non-rounded answer in another task, so that's why you have 2 functions instead of 1. For some reason, when I did this in Dyalog, the editor insisted on expanding one of the numbers and making it 20 digits long. That was very annoying. But the reason I bring up this problem was because that is so neat. Honestly, it was not obvious to me at first. I thought about how should I deal with plus minus, and then when I somehow did this, yeah, it's beautiful. It's so not only is this probably the most obviously readable way to do this, but it's also general. This is not a special case, and that really makes it much better in my mind. Yeah, I like trains. I think I will actually do all of the physics problems in order. They were the easiest set. The problem sets were so I did all of them in the end because I liked it. But they were a very sort of the physics one was easier, and the crypto one was harder. And the neural network one was somewhere in between, I guess. But sometimes with the problems, just sort of reading the description and trying to figure out what you were supposed to do was a big part of the problem. But I'm sparing you that because it doesn't make for a very good presentation. So I have sort of rewritten the problem statements a bit. So in this one, you had something called a grid. It's a character vector, no character matrix. It can have boxes or dashes or crosses. And then you're interested in the shape made out of, so sort of the shape the boxes make in your grid. And you don't really care for the dashes or the crosses. So here are four grids with different shapes, which you might recognize, maybe. And we are interested in some properties of these shapes. So a shape is symmetric if you can sort of rotate it half a turn and it stays the same. And it's contiguous if it's if all boxes are adjacent. And it's valid if it is both of those things. But this is not a formal definition. This sort of is a loose definition at best, especially the contiguous criterion. But that was kind of also the problem. So the solutions to the problem was to specify formally in APL how to do this. Oh, and this is, so that's why I did 4 of them. So I can have examples of all of them. So contingency doesn't work diagonally. It has to be horizontal or vertically. And also symmetry doesn't have to be it doesn't have to be centered in the grid. It can be off-centered. So the first task was about symmetry. This is what I did. So first I consider only boxes. I think the reason there were dashes and crosses to begin with was a bit of a red herring. I don't know. And then you cut out the shape. So so you center the sort of the shape. And then you compare the vertical and the horizontal rotation. This is probably my second favorite train from what I submitted. It looks cool. It's like a Death Star and beams coming out. Contingency was a lot harder, for me at least. So my first idea was to try to implement some kind of disjoint set, union find kind of data structure and use a reduce and stencil to successively merge cells. But I didn't like that. Union find it's a really cool, but it's also inherently stateful, which and I had a feeling that it would take quite a bit of code, so I just didn't write the code. I had the idea, but then I didn't bother implementing it. But after a while, when it had rattled around in my brain for a bit, then I came up with a much better idea. So instead, you consider the shape as a graph, and what I mean by that is to sort of take one of the shapes and zoom in a bit. I mean this. So your boxes are your nodes, and they are connected if they are adjacent. And to make it more, a little bit more concrete, we will name our boxes with their coordinates. So there we go. This is not too hard to do. So once again, you just consider the boxes, and then you compute the adjacency matrix for the graph by doing the selfie outer product with the property of being close. I do include self loops in this, so it's not a graph proper, I guess. But it works out good because when I so the thing with adjacency matrix is that if you have one and you multiply it with itself, you get a new graph modeling the relationship of having a distance of a path of distance 2 between any two nodes. But actually, if we have self loops, it will be a distance of 0, 1, or 2. And if we multiply again, it will be 0, 1, or 2, or 3, and so on. So taking the least fixed point, we get the transitive closure quite easily. And once we have that, we know that, well, if the graph is connected, then we should end up with a complete graph. And a complete graph is all ones. So that's easy to compare against. I was very happy when I found this solution, that I didn't have to write like mutation and but then when I look at it now, I think that maybe the the selfie Swedish tilde should have been inside the power somehow. That would have been better. Yeah, that probably has a fancy name. I'm sorry. I just recently learned that these are called defuns and not sort of curly bracket functions. The takeaway for me was that if your problem domain has some connection with the linear algebra, then you should probably exploit it. Validity is super easy once you have symmetry and contingency. It's just that, and it could not be more readable. I even think this is better than mathematical set notation, because in set notation, once you move from sort of elements to sets, you have to change notation from the wedge to the union. But in APL, you don't have to. Yeah, I'm doing this a lot quicker than I anticipated, but I have a lot of problems. So that's if you enjoy it, I don't know. Yeah, so this is mostly to get to the next one, because we will need this. Anyways, so you have a matrix, probably a large one. I think the examples in the were 40 by 40. Well, that's not large to you, but I don't know. And they are ones or minus ones, and then you're supposed to calculate something. Once again, some physics thing. I think this is smaller than the thing before, but I'm not totally sure. But you get the formula once again. So you're taking the sum over all adjacent pairs, and then you are negating it. And actually, this negation was left out of the examples in the. So the examples were wrong from the beginning. But this was pretty much made I felt, for a stencil. I don't think this is as concise as this could have been. I remember being a little bit bummed that I had to do the each on omega and the transpose omega instead of. I wanted to have the each inside on the 0, 2. So I do like each of 0, 2, and 2, 0. And yesterday I figured out that maybe now that I've learned a bit more, I can actually get that working. But then I didn't even get this working for some reason. So that didn't work out very well. Maybe you guys just see what is wrong here. I'm not sure if I think this is what I submitted, but I can't get it working now. Anyways, So that is used in this problem, which is very, this is well specified compared to the other ones. It's sort of do this, write a simulation, you take an initial lattice. Well, you don't actually take the lattice because you're given the lattice, but you know its size. And then you choose an element and flip it, and if it and calculate the change in energy, I guess. And you accept it either if it's negative or with some probability if it's positive. Do this n times. Return the new lattice. I think it should say not map. And I could translate this literally. So I pick an index and I flip the bit. I love that you have the @ operator. That's it's really nice. The only thing with that operator is I don't really see why you cannot use both indices at the same time. You have to do one. At least I never managed to. I think it has to be a vector, I and j, or like, yeah, something like that. I calculate the total energy for the old matrix, no, the new matrix and the old one, yeah. And then what is nice is I even get to merge the two conditions on keeping it or throwing it away. Because it turns out that if it's negative, yeah, the comparison will always be true. So then you don't have to worry about it. This is super nice because it mirrors the definition almost exactly. The downside is that it's really, really slow because you have to copy the matrix each time since you need to keep the old one if you're going to do that, and you know. So I guess you can use this as a reference implementation for your faster code later on. Or maybe if you don't care about performance, just about price money, then this has also worked out great. Let's not do that yet. Since I have a... Let's do another one. Does anyone have any requests? I wanted to do the neural network thingy, but when I prepare the slides, it is quite complicated to explain, and I only remember it. Like, I remember what I did, but not why anymore. We can, okay, I'll do, okay, the cracking or the encryption. Well, we can do both. We can start easy. So that is problem set. The XOR is in the first problem of the first problem set, I think. I'll just go there. Oh yes, didn't even crash. Okay, yeah, this was not that. Here is the first one. This was a little bit too easy. Exclusive OR is just addition in C2. This is a funny kind of thing, notation-wise. That's not this either. Let's see. Here we have encode. That's getting to the encryption stuff, right? So this was, I think, like the other problem was about sort of discovering stencil. I think this was about discovering encode and decode, because that's pretty much all you need. And then you also need the inverse, even though they didn't tell you. Oh, and also I did, that was not part of the this is not what I submitted. This I did when I prepared my slides. I was like, this should be a train, and it looks nicer as a train. It turned out. No, sorry, this is not the encoding. This is the actual encryption. Where did the UTF-8 bits go? Whatever. I think this is the fun part. So you're supposed to, you did your encryption, right? But now you're supposed to undo it. Maybe you forgot the password. But luckily, you're very bad at choosing passwords. I had a lot of interesting ideas about how to do this. But that felt a bit unnecessary. So the key space is super duper tiny. So it's very easy to just generate all possible keys. Okay, check. Generate all possible plain texts. Check. And then I score the plain text according to the collinearity sort of their character distribution. So the way I think about this is that the character distribution is a unit vector in 26 space. And then you have the character distribution, which Wikipedia claims is holds for English. And for each plain text, I think what I'm calculating is the cosine of the angle between those vectors. And then I pick the one that is closest. But there's a big disclaimer on this. I'm not a statistician. I have no idea if this actually has merit, but it worked, so that's good. I'm also doing some unnecessary stuff like sorting everything when I only need the index of the maximum. But it worked. It was quick on my machine, so that's fine. The next one is one I didn't prepare. So let's go somewhere else. Let's go back to the GCD maybe. I think that's okay, I'll just restart here. Oh yeah, here we go. So one of the problems was write GCD but make it work for arrays. Okay, and the thing I came up with looked like this. So I have done the colors wrong. I'm sorry about that. But basically, you take the difference, or the distance, not the difference. And then you take the minimum, and you recur until you get only zeros in one of the arguments. And that, I thought it was pretty neat when I wrote it. When I came back to it, I think it's a bit incomprehensible. But the problem with doing, so this is like the usual way to do GCD, right? But the problem is that you might get oscillations. So you get zeros, but they move back and forth. But there's actually nothing to stop you from using rank, and that works fine. I think that should have been the solution. I'm not sure if this would work in parallel. Does max work in parallel? I think it's doable with bit hacking, but maybe not for floats and stuff. Yeah, we did that. Let's look at some more code then. Next prime. Oh, next prime was fun, in a sense. I have a primality, yeah, checking function that does very much it's like very readable. Should be larger than 1 and not divisible by anything in the range from 2 to the square root of n. And the next prime takes successor until it finds a prime. I also find that well, since I wrote it, that might be the reason I find it very readable, but still I can still read it. That is good, right? I ended up doing everything in this, with only defense and only single assignment, no mutability, no thread funds. But that was not really a conscious choice. It's just the way I like to solve problems, I guess. And I actually, before the competition, I had two, well, this is not strictly true, but almost, 2 exposures to APL. I had read Ken Iverson's paper, and then I had also seen the Game of Life, on YouTube. And in that video, it's only defense, right? So that's what I thought that APL functions were. When I discovered thread funds, it was weird.
If anybody has questions,
Yeah, okay.
please go ahead and start lining up.
I'll go to the wrap-up part. I just have a few reflections. I think APL is a ton of fun. I think getting proficient when array manipulation has been challenging, but that's kind of the point. I feel like I'm learning a lot, and I'm learning fundamental things. The funny squiggles and the non-conventional grammar has not been a problem at all. I kind of like it, actually. What I don't like is like the incomprehensible system functions and referencing things by numbers instead of names, and this. That I feel is arbitrary, and I don't want to have to learn it. I'm also still having a hard time adapting to the session, and I've complained to a lot of people around the room about that, I think. Also, as you may have noticed, when I explain the code, I go from top to bottom, but from right to left. And that works fine for reading code, but it's a hassle to write code that way. I actually spent an afternoon seeing if I could change the APL Unicode characters to be right to left in my Unicode database, but that turned out to be way too hard. And then yeah.
All right, so basically I have only one comment, which is I absolutely love these slides. These are great. Yes, these are like. And other than that, I also like that comment about the linear algebra, because at least if my linear algebra instructors were correct in the way they described linear algebra, pretty much everything has some linear algebra to exploit. So.
Yes, and even if it does not, if you're an engineer, linear algebra is what you can actually work with, so then you approximate stuff into linear algebra, I think. Yeah, exactly. Sure. Okay, yeah, not just engineering. The slides are unfortunately not done in APL, but if it's any consolidation, the maze on the first slide was done in APL.
Just 2 comments from your presentation. First of all, I think the insights are wonderful, and your coding style is elegant, and I think most of the people here would have trouble improving on what you've written there. Thank you.
Thank you.